Hello and welcome back to the lab. Before we get started with today's video, I wanted to update you with a project that has occupied most of my weekends over the past several months. Um, Training for the MS-150, the Texas MS-150. It's really a 180-mile bike ride, a 2-day charity event that raises money for the National MS Society. The Texas MS-150 is a 2-day, 180-mile charity cycling event. This year, about 5,000 cyclists participated, and I participate every year. This year, I managed to raise about $1,400 for the National MS Society. Here I am, crossing the finish line on day one. That was 100 miles. I was pretty tired. I stayed overnight in a tent in LaGrange, Texas, continued on, and after 80 more miles, crossed the finish line in College Station, Texas, and I did the traditional victory pose. So now that that event has been completed, I have more time on my weekends to work on my other projects here in the lab. And so let's get started with today's video. So on the bench today, we have the HP740B DC standard differential voltmeter. This is a project that I started almost a year and a half ago and did some work on it, and some other things came up and I put it back on the shelf, and I'm finally getting around to getting back to it, and hopefully I can get it up and running rather soon. The HP740B DC standard differential voltmeter is actually 4 different instruments in one enclosure. I mean, it really can be configured to be 4 different instruments inside one enclosure. It reuses most of the same circuitry for each of those 4 instruments. Primarily, it's used as a DC voltage standard. It has 5.5 digits or 6 digits of resolution. The first 5 digits are indicated on the Nixie tube neon displays, and the least significant digit is indicated by reading off the meter for the 6th digit. The output of the DC standard is a precise 6-digit resolution DC voltage in ranges from 1 volt maximum to 1,000 volts maximum in 10 volt in times 10 steps. That voltage is available at the output over here and is used for calibrating DC voltmeters. I used one of these almost daily when I worked at Hewlett Packard in the 1980s to calibrate DC voltmeters of 3.5, 4.5, 5.5, and sometimes even 6.5 digit voltmeters using this DC standard. Not this exact one, but this model number of DC standard. I used it in the 1980s for that purpose. In addition to being a DC standard for calibrating voltmeters, it has other functions. It can be used as a standard, an ordinary zero-center DC voltmeter, analog voltmeter with zero center, so it can read plus and minus voltages without reconfiguring the input terminals. That voltmeter has ranges from 1 millivolt up to 1,000 volts, which can be selected with the range selector switch here. So you can measure as low as 1 millivolt and as high as 1,000 volts using the DC voltmeter function of this instrument. It can also operate as a DC differential voltmeter, and what it will do in that mode is compare the voltage of the DC standard that's internal to the instrument with an externally applied DC voltage, and the meter will indicate the difference between those two voltages. So you dial the DC voltage from the standard until the difference between the two is 0, and you read the voltage of your unknown voltage that you're trying to measure directly off the Nixies with the final digit of resolution read directly off the meter. So that's the differential voltage uh, voltmeter function of this instrument. That operation is very much similar to the HP 3420B that I demonstrated in one of my earlier videos, and I'll put a link to that in the description of this video as well. But it's primarily used as the DC standard. Now I mentioned that it has 4 different functions, and I only talked about 3 of them. The fourth one is it can be used as a DC voltage or DC power amplifier. When an input is applied at the input terminals, it will amplify and provide an output voltage at a higher current level at the output terminals. So it can be used as a DC voltage amplifier. So that's the fourth function of this instrument. HP made the 740B from 1967 up until 1977. So about an 11-year span when they manufactured this instrument. During that period of time, they manufactured less than 2,000 of those instruments altogether. So they're really quite rare. The serial number on this one is 1729. So this is the 1700th voltmeter, and this one was manufactured in 1976, towards the end of production of this instrument. So one could assume that there's a total of less than 2,000 of these units that were ever made. So they're really quite rare. Now in 1977, this instrument listed for $4,500. And that is about $24,000 in today's money. So it's a very valuable, very expensive, very highly prized and highly sought after instrument. They're quite rare. There's less than 2,000 of them altogether. Some of them do come available on occasion, and that's how I managed to acquire one. When I went to acquire one of these, I posted on social media that I was interested in buying one because I had used one at HP back in the 1980s, and I wanted one for, basically for nostalgia reasons, right? And within an hour, someone responded that they had one available, and he said to me that he couldn't let it go for less than $100. Now, I didn't want to cheat the guy, so I actually offered him $200 for the instrument because he only wanted to get $100 for it, and I thought it would be worth much more than that, since really it's the equivalent of a $24,000 instrument. I would certainly be willing to pay $200. So we made a deal, and the instrument arrived here. When it got here, the window that the Nixie tubes indicators show through was delaminating, and there's a polarizing grating that's on the laminator to the rear of the plexiglass plastic window, and that oftentimes peels loose and causes the window to be cloudy and foggy, and you can't really read the Nixies inside of it. So I replaced that window with a piece of plexiglass of the same amber color and resolved that issue. Now, because these are rather rare, Hewlett Packard, I'm not sure what the reason for that is, but HP did not put the input and output terminals directly on the front panel of the instrument. They decided when they built this instrument to use cables that plug into the inputs and outputs with an external box for those terminals. Now, because they're so rare and the terminal input and output cable assemblies can be disconnected, in all likelihood, they have been disconnected and lost throughout the years. So if you can even find one of these instruments, they almost always appear without input and output cable box assemblies. So you have to manufacture your own. And that's exactly what I did. Because I started working on this a year and a half ago before I was making videos. I don't have videos of that process, but I do have the cable box assemblies that I did manufacture. So here is the output cable box assembly. Here's the connector, and here is the output terminals. There's a high and low output terminal, a high and low remote sense terminal. You can do remote sensing like a 4-wire type situation. There's also a guard terminal and a earth chassis ground terminal. So there's 6 terminals on the output cable and a connector on the other end of the cable. There's a high voltage indicator. This is a standard neon light bulb, an NE2 type neon light bulb. So when there's enough voltage present at the output terminals to ignite, to illuminate the neon light bulb, something like 90 volts or 100 volts, I guess, that bulb will light up, warning you that high voltage is present. You don't want to stick your fingers in there. That's what that light bulb is for. This connector on the original unit, these were Deutsch connectors, very high quality, high reliability, military grade connectors, which are not available any longer. So I replaced the connector on the front panel with this amp connector, which is available. It's not really high quality or high reliability. It's plastic, and it's also not really rated for 1,000 volts DC, which it should be. But this is what's available today, and I'm hoping that it will work. So I've mounted the mating cable and to the cable and to the front panel, and they simply attach on, hopefully. There we go. And you turn the little threaded collar around the outside about maybe 3/4 of a turn or something like that, and it threads down and attaches tightly. So these amp connectors are what I will use to replace the original connectors that come with the instrument that are no longer available. I'm hoping that these, even though they're only rated, I believe they're rated at 500 volts. They're not really rated at 1,000 volts. But the way I've wired them internally is with large separation between the high voltage conductors, and hopefully it should be okay. Now the instrument is not really really working right now, so I can't really test that out. But in any case, I made a similar box for the input connector cable assembly to replace the missing cable assembly on this instrument. This one has a high and low input terminal, as well as a guard terminal and an earth ground terminal. There's a switch on here to switch between infinite input impedance and 2 megohm input impedance. What that switch is used for is because it basically has an infinite input impedance, this instrument over here at the input terminal. Any stray capacitance that's on here, in fact, there is a capacitor mounted in here to reduce noise spikes and so forth, but any stray capacitance, even in the cable, can hold a charge. And because you can measure up to 1,000 volts with an infinite input impedance, that stray capacitance and the capacitor that's in here as well can hold that 1,000-volt charge. And not only can you get zapped, even though there's no longer DC applied to the instrument, but you can also damage whatever you're connecting to the instrument, because that 1,000-volt charge could still be on the input capacitance of this instrument. So they recommend that after you make a measurement, you switch to the 2 megohm position, and that shunts a 2 megohm resistor across the input terminals to discharge any voltage that's on the stray capacitance in the input. And then you can switch it back to infinite again, and it will still have an infinite input impedance. Likewise, this I tried to make these cables and these input connector boxes match the originals as closely as I could in terms of color and shape and size. I actually used original Hewlett-Packard binding post banana jacks for these input and output terminals, um, but the cables themselves were not available, and I had to make do with what I had. So this input cable also attaches in a similar fashion. If I can get it lined up, there we go. Um, Line it up with the key and then turn it about maybe 3/4 of a turn and it locks into position. So that's the input cable box and the output cable box for this HP740B instrument. Now I've done some other things internally to the instrument. Um, Inside the instrument, there are actually two mercury cell batteries. One is to add a tiny DC offset for the zero adjustment, and that one is located up in this part of the instrument internally. And there's another one that's internal to the instrument towards the rear on the underside, and that one is used for part of the calibration and testing procedures internally to the instrument. I have not replaced that one as of yet. I simply removed it and shorted that out because it's not used during normal operation of the instrument. So I put a piece of wire in there and make it a 0-volt battery for the time being. I will end up going back in there and replacing that battery as well. I replaced them with the new lithium coin style batteries, and I'll show you that in the next video. So does it work? Not really. Um, Clearly, it lights up, and I can get the meter to move. So some parts of it work, but most of it does not actually work. I have a lot more work to do on it. Internal to this instrument, there are also two photochopper assemblies, like we've seen before on some of the other HP instruments I work with. They're very similar. There are two of them because there are two different high gain loops internal to the instrument, high gain amplifiers that need photochoppers to convert the DC voltage into an AC voltage and then back to DC again. Those all had burnt out neon bulbs, and I did replace those neon bulbs, but I have a feeling that the new photochopper neon bulb replacements are not the correct ones, or something else is going on there, because I have a feeling that the photochoppers still are not working properly. So we have to take another look at that. And we will do that again in the next episode. So will I be able to get it working? I certainly hope so. I certainly hope so. I really love this instrument. I really always wanted to have the 740B DC standard because I used it in the 1980s when I worked at Hewlett-Packard. It was already an old and obsolete instrument, even at that time, but I used one almost on a daily basis. So I would absolutely love to get this one running again. So stay tuned, and hopefully we'll get it opened up and do some more troubleshooting and find out what's going on with this instrument, and we'll have it finally working and operating again in a future episode. But that will have to do it for today. So thank you very much for watching. Please like and subscribe, and stay tuned for future videos with vintage Hewlett-Packard equipment and other fun stuff. Thanks again.